Welcome back to Algebra 2, Lesson 1.7. We're talking about inverse functions. So we're going to consider the two linear functions given by the formulas f of x equals 3x plus 7 all divided by 2, and g of x equals 2x minus 7 all divided by 3. So we're going to do some evaluation using the skills that we learned in the last couple lessons. So f of 5 equals 3. We're going to plug in our 5 plus 7 all over 2. 3 times 5 is 15, plus 7 is 22, divided by 2 is 11. All right, now let's test d of 11. Some more evaluation. g of 11, we have 2, plugging in 11 for x, minus 7, all over 3. 2 times 11 is 22, minus 7 is 15, divided by 3 is 5. All right, let's try b. So f of 0, we're going to have 3 times 0 plus 7 all over 2. And we're going to have g of 7 halves is going to be 2 times plug in 7 halves minus 7 divided by 3. Oh, I forgot to evaluate it both. So we got 3 times 0 is 0 plus 7 is 7 divided by 2 is 7 halves. And on the bottom we have 2 times 7 halves is 7, minus 7 is 0, divided by 3 is 0. So we have another pair where they send to each other. All right, so this is some interesting implications. So we're going to see what happens when we try to compose them. So first we're going to figure out g of negative 1. We're going to get 2 times negative 1 minus 7 all over 3. We're going to get negative 2 minus 7 divided by 3 is negative 3. And then we're going to find f of negative 3 is 3 times negative 3 plus 7 all over 2, which is going to give us negative 9 plus 7 is negative 2, divided by 2 is negative 1. So when we compose them, a number gets sent back to itself. And this, it turns out, is the definition of an inverse function. So the two functions seen in exercise 1 are inverses because they literally undo one another. The general idea of inverses, f of x and g of x, is shown below in the mapping diagram. So our function f takes an input value a in our domain and sends it to some output value in the range, b. Then our inverse function takes as its input element b in the range of f and sends it back to the same element in the domain of f. And when we compose them and do them one after another, like we did with negative 1 above, we send them in a complete circle back to itself. So this would be f composed of g. All right, so take a second to write all that down, make sure you got it. Feel free to rewind if you need to, and then meet me at exercise 2. All right. If the point negative 3, 5 lies on the graph of y equals f of x, then which of the following points must lie on the graph of its inverse? All right, so let's think about input and output. So we have our y equals f of x equals, it's going to have the point negative 3, 5. The input is negative 3, and our output is going to be 5. All right, so based on our picture of inverses up here, what we need is for g, our inverse, to take the point 5 back to negative 3. So our input is now 5 and our output is now negative 3. So if we think of our inputs as x's and our outputs as y's, the point on this graph is going to be 5, comma, negative 3, which is going to be option 3. All right. If a function, y equals f of x, has an inverse that is also a function, we represent it as y equals f to the power of negative 1 of x. Read f inverse of x. It's important to note that the negative exponent on a function does not mean the same thing as it does on a variable. X to the negative 1 is the same as saying 1 over x. It's the reciprocal. But f of x to the negative 1, or f inverse of x, is an inverse function, which is not always a reciprocal. Make sure you understand that distinction. Write down whatever you need to write down. All right, so exercise 3. The linear function f of x equals 2/3 x minus 2 is shown graphed below. Use its graph to answering the following questions. First, evaluate f inverse of 2 and f inverse of negative 4. So we want to know f inverse of 2 equals some number that I'm going to call x, because I don't know what it is. It's an unknown, right? So if you remember what we did in exercise 2, all the way down here, we switched these two when we moved from a function to its inverse, right? So I'm going to do the same thing now. And I'm going to say that f of x equals 2. Because these functions are inverses, so if it maps 2 to x, the other one has to map x to 2, right? Oh, another important note is that the graph that you have in your workbooks is not correct. So you're going to want to make sure to take a moment to pause the video and just copy down the correct line, which I'm drawing in red. This is the correct line. All right? All right, so we're back. So we need to find the value of y, value of x, that is going to give us a y value of 2. So let's find our y values of 2. Value of x is going to give us 1, 2, 3, 4, 5, 6. Right? So f of 6, f of 6 equals 2. What that means is that switching back, f inverse of 2 equals 6. And that's how I do the first one. All right? So I'm going to separate this off from the other one. So now we have f inverse of 4 equals an unknown that I'm going to call x again, right? So now we need f of x equals 4, negative 4. Oops. Watch your negative signs. All right, so we're going to find y equals negative 4. 1, 2, 3, 4. And we're going to get this point here, right, which is negative 1, 2, 3. So now we know that f of negative 3 equals negative 4. And so f inverse of negative 4 equals negative 3. All right. So I'm going to erase some of the points that I made here because it's going to get really cluttered. So just wait 1 second. All right. So on the same set of axes, draw a graph of y equals f inverse of x. Okay. So we could try and calculate a whole bunch of points, but we already have 2 points. Let's just draw those ones. So we have negative 4 comma 3, which is going to be So -3, 1, 2, 3. So here is a point in our graph. We also have 6, 2. Sorry, 2, 6 over here. And then, so those are both going to be points in our inverse graph. So 1, 2, 1, 2, 3, 4, 5, 6. Okay. And remember, once you have 2 points in a line, the line is just going to be drawn between them. Right? So I'm just going to grab, just extend it a little bit so that we have a nicer line. So we pass through these 2 lines, and then we can draw arrows on the end to show that it goes on infinitely. All right. Does everyone understand how? And if we wanted to find some other points, we could do the same kind of calculation to show that they correctly flip from one line to the other. And speaking of flip, actually, it turns out that f inverse of x is the reflection of f of x over the line y equals x. So I'm just going to use this pink line to draw y equals x real quick. So like that. And hopefully you can see that I should also label my graphs. We got f of x here, and we got f inverse of x up here, right? We can see that these two things are mirror images across this line. And so they've been reflected through it. And even on the other side, they're still reflections. So if you don't know how to calculate the inverse yet, which I think we're going to get to later in the year, you can always just reflect it across the y equals x line. Exercise 4. A table of values for the simple quadratic function f of x equals x squared is given below, along with its graph. All right, these seem pretty good. Graph the inverse by switching the ordered pairs. All right, so first we're just going to switch all our pairs. So we got 4, -2, 1, -1, 0, 0, 1, 1, and then 4, 2. Okay. So we're going to plot 4, -2, 1, -1, 0, 0, 1, 1, and 4, 2. Then we're going to connect our points, and we're going to get this shape. And then I'm also just going to put our same y equals x lines that you can see that is symmetrical across that line. If you tilt your head, you can sort of see it's been like reflected like in a pond. All right. Is the inverse of f of x also a function? So we're going to check with this with our vertical line test. I think you should be able to see pretty clearly that at almost all points we're going to have 2 places of contact everywhere except 0. I guess over here, but so this fails a vertical line test, so the inverse is not going to be a function. So we cannot call it an inverse function. A function will have an inverse that is also a function if and only if it is 1 to 1. So a quick way to know if a function has an inverse that is also a function is to apply the horizontal line test. So just going back up, I'm going to try and apply the horizontal line test to my y equals x squared, my original function, which I'm going to do in green. This function, right? So I'm going to try my horizontal line, and immediately it's going to fail. So because this fails the horizontal line test almost everywhere imaginable, its inverse is not going to be a function. It's going to fail the vertical line test. All right, so work on the independent practice, and we will see you soon.